It's so no one's making a profit off of this.
I'm aware of that. So what happened is the following. I can say something. So back in 2014 or 15, like first time when I taught the introductory level physics here, and I had this choice which textbook to take, and usually there is a committee and all that. But I said that, oh, I don't want students to pay so much. And I looked around and OpenStack sounded great actually. So I was very much into it. So I convinced the undergraduate committee here that I would like to experiment with this. And they allowed me, and I did this. In fact, it became such a, reasonably big news that it came in the news here, Egyptian, that, oh, someone is using a free textbook. But then, honestly speaking, eventually down the line, and when I decided to use it, I went through the first 3 chapters, read through it. Oh, these are good examples. Oh, I can use this. Physics is not very different. But then as I went ahead into the book, examples quality really went down. And by the time I reached the 2nd semester, it was not at all okay. So I stopped using it right in the next semester.
Right.
So,
I use it for they have the reference, and then everything, the examples that I do and the things that I focus on are all me.
So then it works, exactly.
Because I pull a lot of,
that's
Resnick,
okay. That's good then. So what I eventually did is that, and then from the next semester on, I was still into this. So I said that you can use any textbook you want, right? This is what I'm going to teach you guys. But if you want to follow a book, you're allowed to teach any book. Books are pretty much the same. And I give only one reference, and that is the OpenStack's book. I don't say that I don't like it very much, but surely it's a great initiative. But I think they need to put in a lot more effort. Like Halliday and Resnick, for example, is a great book. There's no wonder that it got hit. But then not every textbook is great. And I was warned about this by some few people, but I still thought that free option is such a big drive that I was ready to experiment it.
If I relied more on the textbook, that, and so in some classes you have to, especially if I was, especially at a larger school, if I wasn't the only person teaching physics, we'd have to go with a commercial textbook. But since it's my department, and so I can pull out of every resource that I want to for these classes.
Got it. Yeah.
So it provides a framework.
No, I agree.
But the problem is that working with, especially with McGraw-Hill,
He told
with you paying as much more as you're paying, they make nearly as many errors and
understandable.
Halliday Resnick is still solid. They still haven't let their standards drop.
I would say, I have complaints against that also. I think they took away all the good examples. See, they had, I think they had a very selected set of examples, like say 10 to 20 each chapter, 10 examples and then some problems. But all the really challenging ones, which was really thought-provoking, they took it off. And now they have really watered down book, I would say, but still great.
Yeah.
Compared to other books, it's way ahead. But I would say the 2nd edition is significantly better for I would say a ambitious student.
Sure, I'll have to figure out what edition I have at home.
Might be the first one.
Dark. It's not even like a normal binding. It's more like a cloth.
Actually, it's the 1st and 2nd. I don't know whether I was using the original edition or not because it was back in India. It's small. That's like a.
This was a small, but it was still it was probably still this big.
It's like this. Yeah, it's this size and maybe slightly longer. Yeah. But and maybe that's what got into my head. I always say that a textbook should be carryable in your hands, not like these introductory textbooks. You're weighed down by that. But that's just a stylistic
Well, I think the other thing is the smaller your textbook gets, the harder your class.
Okay, that's
You know,
a good point, actually.
we had this textbook for complex analysis,
Oh, yeah, I know those books.
and it was like 45 or 46 pages. That one's really small.
The really hard class, you get a pamphlet.
Yeah.
There's no textbook. This is all research material.
But the best part is, it was only like $6. $6 or $7, I don't know, one of those. I think with taxes, it was around 7.
Okay, so we should go ahead. Hello, guys. Jordan, Luke, Michael. So we have 3 + 3, 6. Oh, we're still with missing Khaled and Aliyah, right? 2 people missing. We have 8 here. Okay. Oh, sorry. I have to set this up today. Has anyone started on the math methods? So, is it reasonable? It's too hard.
Yeah, we were working on it. Pretty much
It's reasonable, right?
Yeah.
Without your glorious leader.
Well, he's our glorious leader for EMT.
Oh yeah, you're not in the. I should also say that if you look up my very old lecture notes, I think 2014 lecture notes, it might be available. I think it's at that time I used to really do this. I used to go at a much faster pace. So that's another place you can look for it. Because again, the idea is to learn, and you can use anything you want. So I think I've done it. Yeah, maybe later on I realized that I should have done that link also. So let me see. If I can figure it out. There will be a homework 9, which will be due on next Friday. So it's what, 6 + 7, it's 13, I suppose. And there is a midterm 3. And this will be a take home too. I know one question that I mentioned I've asked, but I have to think about it. Okay. Any questions or comments in general? Okay, so today we want to talk about Kramers-Kronig relation. Try to I think it's Kramers. This one name. It's not Kramers. It's not apostrophe. Yes. Okay. So, what is it about? So here it is. So this is. So we have Maxwell's equation, which is divergence of the electric field is equal to charge density. And we also said that if there is a material, this is effectively the same as giving the dipole moment density. So if you have a material, you don't talk in terms of charges because the material is typically neutral. You talk in terms of polarization, which is dipole moment density. This is charge per unit volume. This is dipole moment per unit volume. And again, given a dielectric material. And most of the examples we have covered, we said that we talked about a material which has a permanent polarization. But now we want to talk about what if doesn't have a permanent polarization. That means they're all on an average, they are all in arbitrary direction, right? Negative, positive, negative. So on an average, it's all zero. But if I were to put an electric field, not necessarily uniform, right? If I put an electric field, the tendency will be, there will be a tendency to align. And that alignment now should be, it's a property of the material, like especially like, how do you say this? So for example, what's the example? While I was driving, I was thinking of an example. Hold on. So I have an electric field that is coming in, and something wants to align with it. Yeah, think of it. Maybe, yeah, it's not the example I was thinking, but still, if you have a pendulum, it's actually oscillating. Right? So that's a simple thing that is going on. And now let us say there is a wave that comes in. You exert a force, and let us say that's time dependent. There is an oscillation associated with it. And if that frequency is exactly the same as the oscillation of the pendulum, that will be something that will happen. If the oscillation is very large, it's very slow, like you come and touch it and then go back, that will have another effect. And most important is something comes extremely fast. Like something is oscillating so fast that before this pendulum can react, that quantity has gone. Yeah, I think of a pulse. Yeah, I think that was what I was thinking. Think of it as a pulse. Yeah, I think this is what I was thinking. Yeah, so if you have a pendulum, so this is a pendulum, it has a natural frequency. And now think of a disturbance of this kind. Right? This is time-dependent disturbance. So this is some mechanical disturbance. If this is a very small time duration, this pulse has a very small time duration. Before this can react, the pulse is gone. So this might jump a little, especially if this amplitude is very small. It might jump a little, but we might not even realize it. Before something happens, the pulse is gone, actually. The other thing is that this pulse actually gradually goes down. And third one is when it is actually related to this time period. So something happens when the time period of this pendulum is approximately the same as the time of this time, let's say time difference of this pulse. One is when it's very large, when it is very small. And those things, just qualitatively, we roughly realize that, oh, that's going to be different. We want to catch that in here. So there is an electric field. We're not saying that this is constant. So this has a time dependence on it. And that time dependence will actually determine whether this will completely align with it, or if it is too fast, it might just go away and it might not even sense that. It's like let me start with that interpretation. Okay, so that we want to capture that. Let me say that's a qualitative thing we are doing is that, or quantitatively, very precisely, we are going to show that what actually determines this response, if you want. Put an electric field, there is a response, and this will be an induced polarization. So that induced polarization, very qualitatively speaking, I'm going to make this quantitative, very precise, but very qualitatively speaking, this P, that is, I'm not putting the time dependence, I'm not putting any frequency dependence. This is equal just some constant, like not even constant, some quantity times electric field. I'm not putting the time dependence purposely here. That's going to be our project today. In principle, this can also be dyadic. Let's make it simple. Let's say this is isotropic, and for dimensional. Yes.
I was just gonna say, I think there should be epsilon naught there.
Yeah, so I didn't say what chi is. I'm pretty safe here at this point, but for dimensional reasons, for consistency, or just to make this chi dimensionless, let us say, I will put a chi epsilon naught. Okay, it's nothing sophisticated or nothing non-trivial. Okay, so that's good. And notice again, permanent polarization is different. It has its own permanent polarization. But if there is no permanent polarization, you can induce a polarization by putting an electric field. That's what we are talking about. If I put that now in the equation, I notice that I can bring it on the left-hand side. And I see that this is epsilon naught E plus chi epsilon naught E. That's equal to rho. This was just a definition. So let me define my chi to be equal to epsilon over epsilon naught minus 1. And that gives me the equation. Is equal to rho. But we want to cushion all this. Okay, so that's something we are missing in this qualitative way of saying it. I'm missing a lot of details, and that's what we want to bring out. And this is typically defined as the displacement, a vector or displacement field, because electric field has a displacement. And that becomes your Gauss's law in the presence of materials with induced polarization. If there's a permanent polarization, it's still on the right-hand side. Okay? But we wanted to capture this. Okay, so this is what we're talking about. Like again, this is a response, right? There was something here. This was a material property, right? Put in an electric field, it induces a polarization. So what is that P, right? So let me go back there. So I want to begin with that. So that's P. It has a position dependence and a time dependence. Right? In general, that's what I expect. At every time there is a polarization at a point inside the material. And in general, it has time and position dependence. Right? This depends on the electric field and chi, right? So give some space there. I'm going to add on some features to this, right? So there is chi, which will also be a position and time dependent quantity. And there is an electric field, which is also a time and position dependent quantity. Okay. Now, if I have an electric field and there is an induced polarization here, so this is a negative and a positive, that's a polarization at a particular point, that's an induced polarization we're talking about. I can ask, will the electric field at this point, like this is R prime, affect this point? Okay, that will be a non-local system. We don't expect that. Electric field at a point charge is decided by or force on a point charge is decided by the electric field at the position of charge, not somewhere else. Like that's what our understanding of Lorentz forces. One can question those things. Does electric field at a different point affect it? So we assume that it is a local interaction. This is what is meant by a local interaction. We don't expect our neighbor to affect us. It's just a very close region that affects me. So this is decided by R alone here. In general, this could be like this, right? R prime, T prime, right? Exactly like R and R prime. Time also a future or the past can affect me. Right? In general, I can allow the future to affect me, past to affect me, present to affect me. All those are possibility. And we have to add up all those things. If this point can affect, this can also affect, this can also affect. Right? So similarly in time, if present can affect, past can affect, future can affect. So I have to allow everything. So and then I have to add all those quantities. So in general, I have to integrate over all possible positions and all possible times. That will be a very general model. But that's not what we want to do. Just now, as I pointed out, we will say that our prime dependence is not there. In fact, this is R equal to R prime. This is R itself. Right? Why we are assuming locality? Right? So we are saying, so this is a response. So we are saying that the response is local. Local in position. Local in position space. Not about time. We're not saying that about time. And then I don't have to do the integral, right? There's only one point. It's pretty much saying that it's a delta function. So that simplifies significantly. Then I'm left out with time. So this is now a simpler relation. T is equal to minus infinity to plus infinity dt prime, and that is a chi at position. So this is the property of the material that decides how much it's going to get polarized. Like you said, think of a spring in a car versus a spring inside your ballpoint pen. The response of a ballpoint pen for a given force is significantly larger than that of a spring in the car. And this is T, my comma T prime, and then electric field E of R, comma T prime. R is there everywhere, so it seems like position is not really a great for response. It is the time that is important. So I'll stop writing R very soon. Right? But for a few steps, I'm going to keep that. What about T and T prime? Okay. Now notice, if I'm talking about a material, I can start my time today or tomorrow, and things should not change. Right? Whether we, like at a very large scale, we can question that. For example, you can ask, is Newton's law changing with time? Like if you go a billion years back, was Newton's law really the way we write it, or was it different? Like that's a valid question to ask. And as to our knowledge, this is tested to a certain extent, as much as we can. And it is true, especially in the scale of general relativity and all of this true. and people do, for example, speed of light. It's a universal constant. Was it the same 3 × 10⁸ a billion years back? Possibly, and there are hypotheses where you change it with time and how this will affect and what can be observable. And to all measured ideas, it seems to be constant within, let's say, a billion years. That's not, remember, what's the age of the universe, by the way? Age of that? 13.5 billion. Yes, so within a billion years, surely it's a constant. If you go really go past in time, let's say 1 second, presumably there was a Big Bang, and that's what all the data is suggesting, then it seems like very close to right after the Big Bang. We don't really understand it very well. Maybe things were different at the time. So in that context, very similarly, we can say that if I move my time, my loss should remain the same. My response, how a material responds to an electric field, should not change whether I did it 2000 years back or today. So what do I mean by that? So I'm going to change the origin, right? So I would like, so my proposition is that this is not T comma T prime. I want to keep this T minus T prime. And why is that? Okay, so I'm going to change the time now. Let's say I'm going to change my time. So that's tau is equal to t minus t naught. T naught is some constant. That's our origin, right? Instead of measuring it today, so at t equal to t naught, time is 0. Right? So this is the choice of origin in time. Right? Why should it depend on where I choose my origin? Seems to be a very simple concept. But let's see, by making this t minus t prime, I'm going to make sure that this t naught doesn't show up, right, in the equation. Otherwise, it will show up, like where I choose my origin will matter. Like that's called translational symmetry, if you want. Like if I translate my system in time or in position, it shouldn't change. So this would mean that d tau is equal to dt. And in fact, sorry, I don't want to do the d tau in this because t is a free variable, right? The integral variable is t prime. So if I change this, I should also change tau prime is equal to t prime minus t naught. Right? There are 2 times involved, t and t prime. So if I shift my origin, my new times become this. So this is equal to p of r, comma t is tau plus t naught. And that's equal to, now dt prime is the same as tau prime because this is just a constant shift. And when it is minus infinity, the new time is also minus infinity. At plus infinity, it is still plus infinity. And this is d tau prime. That's pi of r is just sitting there. And t minus t prime, now notice, because it's a constant that I'm shifting, that's tau minus tau prime. The constant goes away. That's the main idea. Very reasonably simple. Let's highlight. And that's electric field times r of t prime is tau prime plus t naught. I can define this polarization with a new function, t prime, so that t naught is not there. So this is t prime r comma tau is equal to minus infinity to plus infinity tau prime pi or tau minus tau prime. And so all quantities are redefined so that it is in terms of a new time. So the point here is that if I require translational symmetry in time, which means to say that it should be independent of the origin, then my dependence has to be t minus t prime. I don't have much else. If I don't put that, this will depend on the origin, and I don't want that. I don't want the material to depend on when I'm doing the experiment. Right? That's not a good thing. So that's our t minus t prime. So second thing is that we require translation. So we require translational symmetry in time. And based on these two ideas, now we have, and let's stop writing our R dependence. And in fact, once I stop writing, who says this should be a polarization? In fact, this could be any response. I think of any response in any physics, any system, or any model you're talking about, whatever I'm going to talk about holds. Kramers-Kronig is a system independent concept. So let me stop writing the vector also. Okay, so this is in general true for any response, and the response is some quantity at time t is dependent on some external parameter and the property of the system. Phi of t minus t prime. This is electric field, but we are making this more general. Think of signal processing. Like, a signal comes in and you want to do something to the signal and goes in. So those are all examples of what you can do with this. Okay, that's good. But now one thing is very clear, that chi cannot, or this T prime cannot be very general, right? I cannot have the future come and affect us. Or maybe that's possible, but to the best of our knowledge, future doesn't come and affect the present. It is the past that affects the present, not the future. So we have to impose that, and that's called causality. So now we want to impose causality in this. Causality. And that will be one way to say that is that T minus T prime. So causality is a requirement where you say that chi of T minus T prime has some dependence when T is greater than T prime, but it surely has to be 0 if T is less than T prime. So this is a disturbance. Prime is a disturbance source, right? Prime is a source. This is an observer. The source cannot exist before, or if the, as far as the response is concerned, source cannot exist before the observer. It's not the exist is not the right word. Any source that exists before the observer doesn't matter. That's not going to disturb it. Right? So only the past that disturbs, future cannot affect that. Right? Is that clear, Avinash? Don't seem happy. Right? But then what is this? Right? That's a question. And this is some function, but whatever that function is, I can in fact say chi itself, right? But just to make this very clear, let me say this is a new function. But in this new feature of this new function, notice that this function is specified for t greater than t prime, but it is not specified for t less than t prime. So I can give any property to that function for t minus t prime, because anyway it is 0. That is being forced by that, so it could be anything. So that's we're going to use that in a minute. This feature can be easily put in by saying that this is 0, right? So p of t in that case, so causality is very simply introduced by just introducing a limit on the integral. Very simple idea. If you want to be more sophisticated, which we will have to, because we are very soon going to realize that this simple-minded thing it's completely correct, but it's very hard for analysis purpose. For analysis, we have to go into the Fourier space. So we will say that we'll introduce a step function, a Heaviside step function. So this is t minus t prime is equal to 1 if t is greater than t prime, and it's equal to 0 if t is less than t prime. That's our step function. And then chi of t minus t prime is pretty much step function multiplied by f of t minus t prime. And then I can reintroduce mine. That's another way of introducing this. And we will see that this is better for analysis purpose. So what's the difference? Here I have imposed causality in a very concrete manner, like by bluntly, just perfectly right, nothing wrong in that. Here, what's the difference? I said that this exists, that there is a response of this kind, and this susceptibility, which is the property that decides the response, has to satisfy causality. That's a statement. So it is an inbuilt property instead of explicitly saying that's our only difference. Maybe more precisely, I think we can say this is f of t, right? If this too seems to be confusing, you can say this is f of t, because for t greater than t prime, it's only this that contributes. Right? So then That's very clear that otherwise you would say, oh, these two are the same. That should be 0, which is of course true. Okay, that's all good, perfectly fine, but this is not very useful. Okay, when you're really doing an analysis in your lab, this is not very useful. Why is it not very useful? Because most of the experiments in OPEX are not done with time-dependent quantities. It's done in frequency-dependent quantities. So we want to see this statement of causality in the frequency space or in the Fourier space, and that's the complication in here. So analysis becomes easy in the Fourier space in the sense that quantities are available in the Fourier space, but when it comes to insight, that really goes away in the sense that it becomes convoluted in the sense of an analytic function being, the properties of an analytic function are great, but it might be harder to imagine the connection between the imaginary part of an analytic function and the real part of an analytic function. You need to have a lot of experience in it. A beginner, it's harder for a beginner to interpret those things. And that's the challenge we'll see. You will see that there is something to do with real and imaginary part. Okay, so that's our statement of the problem. So we have 3 approximations. We said the response in space or the position space is local. In time, it is translation symmetry. And third, it has to satisfy causality. Under those 3 conditions, our response, any response for that matter, has to satisfy this with our property satisfying causality. Let's take this to the Fourier space. Let's see what that, how does it look like. So change the code. So everything we are going to do in Fourier space. So what is a general description? If you have P of t, what's the connection between a quantity in time and the Fourier space object associated with it, you do Fourier transform. So this is d omega over 2 pi, and this definitions change as I mentioned before, but we will use this particular definition. There's a minus notice because we are working with time, and the Lorentz symmetry requires that time as a negative quantity relative to the position. Correct. So that's that minus sign, at least in my notation, but it doesn't matter as far as Fourier transform is. And this is P tilde omega. And should I put a tilde? Yeah. This in principle is a new function. This is a P tilde if you want. That's another function relative to P. But I'll stop writing the tilde and I will say that whenever it's a frequency dependent quantity, it's understood that it's a frequency function, a dependent function, and this is entirely different. So it's implicitly understood. That's just being lazy, and more than laziness, I think let's avoid some clutter in the equation. Okay, what's a Fourier transform? So we can think of this as Fourier eigenfunctions, right, or eigenvectors, or unit vectors, if you want to think of this as a vector space. And these are the components of this function. That's the way to look at it. But as far as transformation goes, Fourier transformation one, whether it is this or this is the connection between the two. And you can invert them. And the inversion is t e raised to plus I omega t. That's a difference, and this is p of t. It means that if I know p of omega, I know p of t. If I know p of t, I know p of omega. Both are equally known, similar functions. So most of the time, especially when there is translation symmetry, and you will see why that happens, that you will go from one space to the other, work in the other space, and then come back to the original space. Okay, so that's your Fourier transform. And this is satisfied by chi, right? since chi has a t minus t prime, let me also write that. So chi t minus t prime, right, would be equal to minus infinity to plus infinity d omega over 2 pi e raised to, notice omega, I just had to change t minus t prime, right? This remains the same, pi of omega. There are no, so just because there are t, if it was t comma t prime, then there will be an omega comma omega prime. So this is the advantage of going Fourier. Whenever there is translational symmetry, instead of two parameters, I've got only one parameter, right? Frequency, that's it. So all the time dependence is in there. That's very trivially speaking, that's one way of looking at an advantage, one advantage of Fourier transform. And the same thing again, right? As for concreteness or completeness, this is again this I omega t. So this is t prime. T minus t prime is equal to chi of t minus t prime. If I want, I can substitute this t minus t prime exactly like what we did earlier. Make the substitution and I can get rid of this t minus t prime dependence. Right? So that's a translation symmetry in there. Okay, all that's good, but we have a dependence of this kind, right? P of, so let's look at this P of omega. So we want to see what is the frequency dependence of the induced polarization. Remember, let me write that. So yeah, I write here. So P of t, since it is on the other board, those are online, they cannot see this. So this is chi of t minus t prime and e of t prime. And the question is, what is the relation between this? Right? How does this look like in the Fourier space? And we're going to see that it's very simple, very straightforward. That's first step. Okay. So P of omega is equal to this. So this is minus infinity to plus infinity dt e raised to I omega t times P of t. Substitute P of t, infinity to plus infinity dt e raised to I omega t. P of t is what? P of t. Yeah, that's minus infinity to plus infinity dt prime, right? And this is chi of t minus t prime, right? And field t prime. That's correct. Substitute this, the Fourier transform, right? So this is equal to minus infinity to plus infinity dt e raised to I omega t dt prime. Too many integrals, but they're all going to collapse. Replace this with that. There's already an omega on the left, so I have to be careful that I don't introduce a new omega. So this I'll call it omega prime, because I've already used that one. That's minus infinity to plus infinity. And this was what? Minus I omega prime. And this is t minus t prime. And this is chi of omega prime now. One more, right? Four integrals, right? So this is minus infinity to plus infinity e omega double prime now, e raised to minus I omega omega double prime, and this is t prime and e of omega double prime. move the omega integrals to the left, change the order of integrations. As far as they are convergent, that's perfectly fine to do. Double prime over 2 prime, and these two quantities are dependent only on omegas. Omega prime E of omega double prime. Okay. And we have two time integrals. So I have a time integral et, and let me collect all the time integrals with t. So there's an e raised to I. So these two are a t integrals, right? So that's I t with omega minus omega prime. And there is another time integral dt prime, which is e raised to I t prime with omega prime minus omega double prime. Okay. Any questions on that? Like it's pretty much this is, if you want, this is a property in Fourier space, right? Whenever something is related as a translation, you're going to see that this is all going to collapse. What is this integral equal to? We haven't done it a lot, but we haven't, I haven't proved it, but you're familiar with it? Anyone? What is let's say x e raised to I k x?
Looks like that is the definition of delta function. Should be 2 pi times delta function.
Yes, so this is a 2 pi times a delta function with respect to k. X is integrated out. Like, I'm only going to motivate this. The proof is slightly trickier in the sense. Like, let's do the following. If I were to set x equal to 0, like this is a hand waving argument. It's not a complete proof. If x was equal to 0, let's say this is I, right? If x was equal to 0, I is equal to minus infinity to plus infinity dx. Which is infinity. That should be right. The length of the real line, if you want. Right? It's infinite. But if x is not equal to 0, if this is the harder one to see, is that this is an integral of minus infinity to plus infinity dx cosine of kx plus I times dx of sine of kx. Now that's not very clear what happens, but if you take some proper limits here, minus n to plus n, and if you go in terms of wavelengths of this k, then you can see that this is a periodic function. One has to argue that that's actually equal to 0. One get questions. Right, the proof is a little trickier. It's not straightforward. This goes back all the way to Fourier. Like this became this is one of the things that comes up that is delta function really represented in terms of cosine function or not. But let me not get into that proof. How about this? Read up like extra credit. Read about Fourier and what's the way to, like you might what's his name? Thermodynamics, popular guys in thermodynamics.
Boltzmann.
And
There's many people. I just cannot think of them.
Tom
Dulong, Petit. There's Rayleigh, and there's some guy named James.
hold on. Fourier, one second. There is the internal energy. What is F?
Gibbs.
Oh, Gibbs, yeah, that's Gibbs, yeah, Gibbs, yeah. Gibbs, so it's Gibbs, I think it's called Gibbs paradox or phenomena, maybe. Gibbs paradox or phenomena, I'm not sure. The idea is that if you were to actually Fourier transform a certain functions, like for example, let's say you have this is a simple step function, right? Yeah, simple step function, and you break that into discrete quantities. So this is a f of t, and this is open. At that point, you don't know where that point is, right? Right now, this is the same thing that comes from the delta function, and this became a big controversy, or not controversy. It was very difficult for people to digest at that time. And the point is, if you were to go into the Fourier space, now this it depends on how many oscillations do you want to keep to reproduce this. How many modes do you have to keep to reproduce this? And it turns out there are lots of them, but you will always miss a point. There will be a spike that will be missed, and it was very hard to capture that in the early days. And that's the same idea with the delta function, and this feature shows up here. So it's very hard to prove that, but look it up. At least you will be able to appreciate what's going on. So look up Fourier Gibbs phenomena, and you will encounter this if you're really doing something at a from the scratch. You will encounter this, and you'll be completely confused for what's happening here. So it's a nice thing to be aware of this integral representation of delta function. But I'm not going to go into the details, right? So this is at least in these days, this is very well accepted. So that shouldn't be a problem, but still, especially like you can criticize that for sure, right? And one should criticize that when you're really doing something fundamental. Okay, so if you use that delta function properties, so then I know that this is 2 pi times delta function of omega minus omega prime, right? Whatever is not the integral variable, that becomes the delta function. And this quantity here is 2 pi times omega prime minus omega delta prime, correct? And let me keep rest everything the same. It's infinity to plus infinity omega prime over 2 pi. Oh, this was also minus infinity to plus infinity. Pi of omega prime. Okay, that's what it is. That's good. Now there are two delta functions, two integrals. We know how to do those integrals, right? So collapse it, right? The delta function pretty much collapses the integral. 2 pi's cancel out. And that's equal to omega prime is equal to omega. Wherever I see an omega prime, I replace it with omega. So it's pi of omega. Omega double prime, I replace it with omega prime, but omega prime is omega. Right? So that's also. That's fantastic because there is no integral anymore. In the Fourier space, this is algebraic. The response that we saw, the causal response in the time space is pretty much a algebraic dependence in the Fourier space.
Frequency space?
In the frequency space. Did I say wrong?
Yeah, it says time space.
No, I said the causal response in the time space, which shows up as an integral, which is convoluted in the sense that we have to add up all those quantities. So the integrals are usually hard to manage. In the Fourier space or in the frequency space, it's just algebraic. Right? It's only the frequency that we are talking about matters. Like if you have an incident electric field with a very particular monochromatic incident frequency, the polarization will depend only on that frequency. Very, like it could have oscillated with any frequency it wanted, but it oscillates with only the frequency that the monochromatic wave is coming. If you think of it in terms of radiation, like you have an incident beam coming in, this atom starts oscillating and it emits some radiation. Right? That emission, we are saying, is going to be exactly the same as your incident field. It didn't have to, right? It could have emitted something else, but it doesn't. If it is a causal response like radiation is something more than, and we'll come to that. That's different. That's the next semester quantity. That's more than what we're talking. But this is just a response. Okay, clear? Any questions at this stage? So that's the first step. Now we want to actually look. So, but we forgot that chi had this condition, right? Chi was causal. We had some intrinsic condition in it that it has to be causal. What about in frequency space? How does causality show up in frequency space? So, well, is there any condition on this? Where is the causality in it? Where did it disappear? Right? Where is that condition in here? We had a causal condition, right? That chi should be 0 if time is, if the present is affecting the past, if future is affecting the present, if the future is past, then it's okay. But what about here? What happened to that? We forgot that because when I said this is minus infinity to plus infinity, I haven't introduced causality. Right? In this way of doing it here, I said causality is implicit in chi. Chi has the information of causal. We just said that chi, the susceptibility, is supposed to be causal. So that information is not there. This is just translational symmetry. Any translationally symmetric system will satisfy this. Whether it is frequency, time, or anything, whenever there is a translationally symmetric system, or whenever there is translational symmetry in Fourier space, it will be algebraic. So causality has not been introduced yet. That means that this has some condition. And that condition we want to explore now. And that's what is called Kramers-Kronig relation. The condition that chi has to satisfy over this translation symmetry is what is called Kramers-Kronig relation. And we want to explore that. So let's go back now, right? So I think okay, so summary, right? We want to go slow. Oops. So remember, we are talking about a response. So a response, this is the summary, P of t is equal to minus infinity to plus infinity dt prime, phi of t minus t prime field, and we set that chi has to be t minus t prime. I can just simply write t, right? If I choose t prime to be 0. So that's equal to some step function times some new function, right? Just not to confuse you guys, let me say this. Let me not be lazy. Oh, yes, to run. Okay, so that's your causality condition, but this statement alone, the response alone, we set in the frequency space is P of omega is equal to chi Yeah. And this is electric field in the frequency space, this is not including this. Right? This has not been introduced. So how do we introduce that? So now let's look for new things. Let's also say, so some conditions, right? So first thing is that we say that this property of the material, susceptibility in the time domain, right? This is in the time domain. There's one in the frequency domain, one is in the time domain. This is what is usually measured in the lab. This is the actual quantity that shows up in the Maxwell's equation. This has to be real. Why should it be real? Electric field is real. Polarization is real, right? So the material property should be real. Again, you can question those things. Is it really necessary or not? But if that's an assumption we make, and under those conditions, that's what we will derive. So let's say that chi is real. Or instead of saying chi is real, let me say f is real, right? If chi is real, then theta function is just 0 or 1. So this has to be real. Right? F of t is real. That's a assumption we make. And then the question is, so what does it mean to say that f of t is real? It means simple, right? The f of t star is f of t. Like this is a complex conjugate of f of t has to be this. But we know that this is going to have a Fourier transform. Fourier transform of a real function, is it real? What is the Fourier transform of a real function? Will it be real? It doesn't have to be because there's an exponential, right? Exponential of I cosine plus sine omega. It doesn't, in general, it doesn't have to be. Then we have to ask, how does this condition, if I say that it is actually a real function, how does the reality of a function in the time domain look like in the frequency domain? What's the condition? We have to explore that. And we are going to show that this is equal to, this is not obvious, I'll show this in either today or whenever we reach here, right? Depends. Right? So this is going to be like this. I haven't proved that, I will prove that. Okay, very straightforward. Okay, that's good. Second is notice I have a step function, right? So chi is given in terms of the function. So this is theta times f, right? Where theta kills the t dependence from the so t has to be greater than t prime, right? So this is t prime, right? So t, if I'm talking about t, and the observer has to be on the right of the source. So I cannot have any, I cannot observe things before, like before I shoot the gun, I cannot ask whether someone is alive or dead in a sense, correct? So this function, whatever this is, chi is, whatever this function is, there's some quantity here like this, some function. There is no information about this because theta is going to kill it anyway. So I have a choice to keep it whatever I want. Right? There is an arbitrariness in the function f that I introduced. So I can choose whatever I want there because anyway it's going to kill it. That's a choice. It's not a necessary thing, but it simplifies our analysis significantly as we go. So you can choose anything we want. So we will choose it so that this is the mirror image of that, the mirror image in an antisymmetric way. So we will choose this to be like this. Right? So exactly we want. So exactly. Oh, I want negative. Did I get that? Negative? No. negative. That's right. So this is the negative of this. So this is, if I can capture this. Right. Mirror. What I mean is that mathematically it's better, right? Sorry.
I think it is called water image.
Odd function. Water image. What? What did you say?
I think it is called water image.
Water image. Oh, because you see, yeah, this is the image in the water. Yeah, good. Water image. Or odd function. Right?
Yeah.
This is an odd function. F of minus t is simply minus of f of t. Okay, so that's a definition of an odd function. So we say f of t is odd. That was just a choice. If one is really doesn't, this is something fishy, then you take out this condition and redo the whole problem. It is slightly tougher, but it can be done. It has been analyzed using those conditions. Okay. So this, what does this mean here? F of minus t is equal to minus of f of t. That's in position space. Again, we are to ask, I put a constraint on a function in the position space. How does it look like in the Fourier space? What does that do? Right? What's the frequency dependence depend on when it's an odd function? And it turns out it's the same. That's equal to minus of f of omega. Again, we will show this. Right? That will be the exercise. We'll do that to the sort of summarizing here. Third one is the hardest, right? Which is the causal relation. Questions? You guys are worried? Both of you. Good. Okay. Third one is the causality. This is real, is not really. This really helps the analysis, but the main is here, which is a step function. So this is causality. Causality in the time domain looks like a very simple function actually, 1 or 0. T greater than 0, t less than 0. Okay. How does it look like in the Fourier space? Okay. And how does it look like? Asked because we did this. Did we do this? Not in this course, actually. We did this in mathematics. Okay. Right? Okay. Don't remember.
You have to answer.
Yeah. No.
I'm waiting for you.
So if you recall, it's not a straightforward quantity. So the step function and the frequency domain becomes non-trivial. It is limit a positive quantity going to 0. That's del F plus. And in principle, it is just 1 over omega. So think of, remember your quantum mechanics, right? In quantum mechanics, you have uncertainty relation, Heisenberg relation, position change of an error in position times error in frequency has to be a constant, right? If the error in position is large, frequency is small, right? Or momentum is small. If momentum is large, position is small. They are usually one inverse of each other. And it has to do with similar thing like it is one is the derivative of the other in a sense if you want. Like momentum and momentum is velocity, right? Velocity is derivative of position. So in that sense, there is a connection there. And so step function, what's the inverse or derivative of step function? Delta function, right? If you look at it as a figure, the step function, its derivative is delta function, right? So in that sense, so if you have something like this here, when you go to Fourier space, it's going to like very roughly be the derivative of that, so something more than that. So you expect it to have a complication there. And this will be equal to I over omega plus I delta. Notice if there is no delta, that's 1 over omega. Right? You already see some infinite structure there. But what is that equal to? Like this, there's a better way of interpreting this. And that is, what is I over omega plus I omega, right? So that's, what is this called? When I multiply and divide by both sides, rationalize this quantity, multiply by omega plus I delta, or minus I delta, and divide by omega minus delta. That's 1. So this becomes limit delta tends to 0 plus, right? And the real quantity here is the one that when I multiply this denominator with real, right? Omega square plus delta square. And the real quantity is delta. So it is delta over omega square plus delta square. And there is plus I times limit delta tends to 0 plus times omega over omega square. Very sensitive limit here. Okay. What is this? Familiar by any chance? Might have done this in one of the homeworks if you didn't pay much attention. Look at it very broadly speaking. We can, again, we will do all this more explicitly.
Is this some sort of like differentiation tangent or arctangent thing?
Possibly.
I think it would be if the deltas are constants.
Tell it again, Jordan.
It would be if the deltas were constants, right? Then you could use.
Then you could use what?
Some kind of arctangent or something.
If you integrate, right? You guys are thinking of if you integrate it.
Mm-hmm.
Right? If you integrate this, yes, you're correct. This has that structure, but this is not having an integration, right? So take the limit. If omega was not 0, what is that equal to? In the limit delta tends to 0. If omega was not 0, let's say 3. If omega was 3, what is this quantity equal to?
1/9. You said if omega is 3?
Yeah, if omega was 3, yes. Take the limit.
0?
I mean,
0, right?
zero
Because
over.
omega was 3, this is negligible.
Okay.
So there is in the numerator there is a delta, so it's 0, right? So if omega was not equal to 0, it is 0. Now let's say omega is equal to 0. Think of delta function, right? If omega was equal to 0, then this is gone. In the denominator, delta square dominates now. One of the delta cancels, so it is 1 over delta, so it's infinity. Right? So this has the features of delta function. In fact, you can show that if you integrate this, that is when your substitution comes in terms of tangent, which is how you see it as an arctangent, then it will come out exactly pi for that matter. So this is actually a representation of delta function. Very non-trivial. So, but we'll see, we'll prove all this, okay? I'm just summarizing. So this is pi times a delta function. That's a causal relation is showing up as a delta function in frequency plus an imaginary piece. This is the non-triviality in going into Fourier space. How do you interpret this? Okay. So these are the 3 requirements, and this is going to impose, so requiring this implies, let us say, that the real part of chi, so chi of omega has two parts, right? Real and imaginary part will be equal to minus of the omega prime times, let us say, minus, and that is a 1 over pi, and 1 over omega minus omega prime. So this is chi of omega square plus delta square. It's not very hard to see where this is coming from. That's this quantity times the imaginary part of chi of omega. If you want to see it like that. And this is omega prime. So if you know the imaginary part of the frequency dependence, because of causality, the real part is fixed. You don't have a choice. Think of analytic function again. Analytic function has exactly the same feature that if you fix, if you give the imaginary part, real part is fixed. So we seem to be saying something about the dependence in chi, and this is called Kramers-Kronig relation. This is a summary. We will next time come and prove how this happens and how we reach here. In fact, this is such a strong statement that experimentally, I should also say in the last few minutes, this has to do with absorption of a material. If there is light, this experimentally is how, for example, water, right? Does water absorb visible light, infrared light, ultraviolet light? Does it absorb all these things? For example, if you were to go down, let us say 500 meters in water, right? It's probably very deep, not survive. But let us say you're in a cage, well-protected cage, and you're 500 meters down in ocean, let's say. Will you see light? Right?
No.
Will you see any other form of light? Like infrared, X-ray, ultraviolet, gamma rays?
You can certainly see like the bioluminescent lights. So like the
Bioluminescence, yeah, but that is right next to you, right? But I'm saying from this, let's say from surface, if I were to shine an ultraviolet light, how far will it go?
not that
Let
far.
us say as I come up, okay, I am deep inside the ocean, I start coming up. Which is the first light that you will see? Which is the first frequency you will detect? I can detect all frequencies.
Probably the highest frequency.
Anyone else? It turns out only visible light penetrates water. Only visible light. No wonder that life picked it. Life depends on visible light. Only visible light is a very sharp beam. That is 400 to 700 nanometers. That's the only thing that penetrates water. Nothing else. This is a big challenge because how do submarines communicate? Radio doesn't go in. Submarines cannot communicate using radio. You cannot use ultraviolet, you cannot use radar, and nothing works, only visible light. Big challenge for submarines. So what they do is that eventually they realize that there is a little penetration in the extremely low frequency, which means extremely high wavelengths. But then if there is an extremely high wavelength, we're talking about kilometers. You need an antenna that is that big. Right? How do you detect that? So you use the whole submarine as an antenna. Right? That's the best you can do. So it's a huge challenge, at least in World War II, where submarine was the big deal, the deciding factor between 1 and 2. Like 2 actually became, there are other technologies that came in, but it was a bit like when it was going on, submarines were a big deal. So the big challenge is how do you communicate in there? But the interesting part is that only visible light goes in. But I was coming back to this, that absorption, right? This has a huge peak, the delta function, all that comes into the picture. But this is modeling, right? And that decides your This is refractive index. So in experiments, it is much easier to do refractive index than absorption. So what you do is you use Kramers-Kronig to get the, earlier you had to check it, but now it is so well standard that you don't even bother to do it if whenever you don't know. If it is hard to measure absorption, you just use this relation to get that. We'll come back and prove all this. As of now, we'll stop here. Again, I crossed 7 minutes, but you guys are too nice. Okay, thank you. I think that is correct.
I think you're only over 1 minute,
I think it's 12:15, not
12:15.
12:15.
Oh, it's 12:15. Okay.
But there's only 21, so it's still 6 minutes.
Yeah, I said 6 minutes late. Yeah. He said I'm only 1 minute late, so he was more forgiving. Okay, Michael, Jordan,
5 minutes
questions?
is a grace period.
Huh?
5 minutes is a grace period. It does not count against anybody.
Well, I just was.
No question.
No questions.
I thought we had till 12:20. I don't mind if 5 minutes is.
Yeah, I think you guys, I noticed, I think, for example, Rob runs away, then I think even Luke runs away. I think they have commitments, most probably. Even if you don't, I shouldn't be doing it. I think I take liberties with you guys. Okay, so shall we call it?
Yes.
Okay, Jordan has left. Michael, everything going good? Are you catching up?
Very good. Yeah.
Not just with my course, within general things. Yeah.
Yeah, I'm starting to.
Okay.
I might make it.
Okay. Nice. Take care. Yeah.
All right. See you guys later.
See ya.
Bye, Mike.
Good weekend.